Okay, everyone. So before we start, I would like to repeat a part of the description that I wrote for this talk, just to make sure that we all kind of appreciate the absurdity of the world that we live in. Because somehow, the safest way for us to travel is by getting inside a metal tube, flying 12 kilometers above the ground. And by the way, the metal tube is 50 meters long and 1 millimeter thick. And the funny thing is that it's not even close. A couple of notes on this graph. I've decided not to include motorcycles because the bar would be so long that it would disturb the people in room number 6. And I haven't forgotten to include the plane bar. It's there, it's just not very large because the number is 0.002. If you do the math, that works out to about half a pixel. Half a pixel doesn't really make sense in this context, so I've been generous and doubled it, given you a full pixel. My name is Jakob Endrestad Kielland. Despite what it might look like in this photo, I'm actually not a pilot. I'm a developer who works for Variant in Trondheim. And luckily for me, and I think even more luckily for you, because you've just dedicated an hour of your life to listening to me talking about aviation, I have a dad who's a pilot. As you can see, we're a very fashion-forward family. And this talk is inspired by my lifelong interest in aviation. I remember as a kid, one of my favorite interests would be for us to go to the airport and just sit there and watch the planes for a while. And so all the conversations that I've had with my dad about our various industries, about the similarities and the differences, is what has led to this talk. Oh, sorry. And so, of course, he's been a hugely important resource because not only is he a pilot, but he has worked in accident investigation as well. He's also written the book on an airplane. Literally, Widerøe were the first airline in the world to take delivery of this airplane, and he was a part of the working group who wrote the procedures for it. And so, suffice to say, this talk would never have happened without his help. And when I told this story to NDC, they were kind enough to give him a visitor pass, so he's actually in the audience today, something that means a lot to me. And another consequence of that that's very important is that you need to all laugh at my jokes so that he thinks I'm funny. And so this talk is going to have 3 main parts. Those parts are called people, proficiency, and procedure. And in all of these, we're going to go through how aviation approaches a certain topic, the topics that you can see here, and look at what kind of things that we can take away from that, what we can learn. And so, of course, these didn't all start with P initially. 2 of them did, and the other one didn't. I'm not going to tell you which one didn't, but now they're all nice and similar, right? And so we're going to start by talking about people, and specifically, we're going to talk about how people work together, so teamwork. Because it turns out this is really important for safety in aviation. And so because of that, for the last 50 years, aviation has worked systematically to just do teamwork as well as possible. And there's really no better demonstration of that than United Airlines Flight 232. And so this was a flight served by a DC-10, one of these 3-engined airplanes, that took off at 2:10 on the 19th of July, 1989. And so it took off out of Denver, and it had a crew of 3 people. This is not especially common anymore, but back in those days, systems on airplanes were a lot more manual, so you often had a flight engineer in the cockpit together with the pilots who did some of the things that are automatically handled today. And so as you can see, by the number of flight hours for each of these people, it was an extremely experienced crew. And so they were headed for Chicago, and about an hour after takeoff, United Airlines 232 experienced an engine failure. And so while it's very rare, jet engines do fail sometimes. The one that you can see here, this is a more modern engine. It fails roughly once every 1,000,000 flight hours. And actually, it's not usually as dramatic as you would think, or to put it in terms that those of you who have watched Chernobyl will understand, it's not great, not terrible. And the reason that is not terrible is actually twofold. The first one is that all multi-engine airplanes are designed to be able to fly with at least one engine shut down. So what you'll actually often see is that even if a plane experienced an engine failure, it might just continue to its destination because it's totally safe to do so. And the second reason, which is more relevant here, is that an engine failure is almost always what's called a contained engine failure. And so what that means is that if there are fragments, they only exit through the back of the engine. They don't impact the plane in some other way. And so this failure doesn't cascade to the rest of the airplane. And what happened with United 232 was that it experienced an uncontained engine failure. And so what really happened was that the fan disk cracked. And so you know when you're looking into a jet engine and you see this big fan, right? Like all of those fan blades are connected to a disk in the middle. That disk is kind of important. And due to improper maintenance, in this case, a crack had formed, and finally the disk split in two. And so you had a bunch of fragments and fan blades that were shot out at huge speeds and ended up going through the engine and hitting other parts of the airplane. And so in the cockpit, at this time, the pilots can feel the plane just shake a little bit, and they notice that the number 2 engine shuts down. And so procedure here is to try to restart it. Of course, you'd like to have the engine back. But they realize very quickly that there are no signs of life here, it's not gonna work. And so what they do is they pull the fire handle. And what that does is if there are any fires in the engine, it shuts them, like it extinguishes them, and it stops like the flow of fuel and oil and stuff to the engine. So this is common procedure when you realize that an engine is not gonna be able to be restarted. And as the captain and flight engineer are discussing this and going through these procedures, the first officer notices that the airplane, which was in a slight right turn when this happened, keeps banking more and more to the right. And he pulls the yoke to the left, but nothing is happening. And so to move the control surfaces in huge airplanes like these are really, really big metal plates, right? So you need a lot of power. And in these airplanes, you use hydraulic systems. And so a hydraulic system needs high pressure liquids to work. So if you have a puncture in that system somewhere, that's very bad because then the pressure is gone and the hydraulic system doesn't work anymore. So because of that, the DC-10 actually has a triple redundancy on the hydraulic system, which means that it has 3 separate independent hydraulic systems that can all fly the plane just fine on their own. And so that's to minimize the chance that something happens to all of these at once, right? And they've even gone further than that, where like the pipes are placed in different parts of the airplane to, like as far as it's possible, to minimize the chance that something happens to all of them. But towards the back of the airplane, where you need hydraulics for the tail and the elevator surfaces, all of these systems kind of have to converge. And so I'm guessing you can probably guess what happens. What happened here was that the fragments from the engine took out all 3 of those systems. And so I've updated my assessment from earlier. So what's the current status? We have an airplane that has absolutely no control surfaces. Moving the yoke or pushing the rudder pedals does nothing. The crew, they see that the right turn is becoming quickly more and more dangerous. They're sitting at about 45 degrees to the right now, which is becoming quite scary because if they end up upside down, then there's absolutely no way they could ever save this. And so they discussed very quickly, and they realized that the only option they have is to apply differential thrust. Because what they still have on this airplane is 2 functioning engines, right? One on the left and one on the right. And so they pull the throttle for the left engine all the way back, and then the throttle for the right engine all the way forward. And by doing this, they manage to slowly restore the attitude of the airplane. But they're not really out of the woods yet. So they call the cabin crew forward to talk to them and kind of brief them on what's going on. And as the head purser, so the head of the cabin crew, comes forward, he brings a message that there's actually a passenger in the back who's an off-duty captain on the DC-10 for United Airlines. He's just here as a passenger, but he's realized that something's gone wrong and alerted the cabin crew and said that he can come forward to the cockpit if they need help. And I think it could be tempting in this sort of situation where everything is kind of on fire to not invite more cockpit, like more chefs, or more chaos, more chefs into the cockpit, right? But that's not what Captain Haynes does. He immediately says to bring forward off-duty Captain Fitch because they need all the help that they can get. He realizes that immediately. And by a bizarre stroke of luck, Captain Fitch has actually studied a similar incident, just out of interest, because a few years before, it gets worse, just wait. A few years before, something similar happened to a 747. It lost all the control surfaces and could only control itself with the engines. It ended very badly in a crash, but he was curious. And so not only has he studied this, he actually went into the simulator and simulated this sort of event just to see if he could do it on the DC-10. This is not procedure, it's just because he was curious. And so by dumb luck, you might have the only person in the world who has practiced these sorts of conditions on this flight. And so off-duty Captain Fitch sits down by the throttles. He takes one in the left hand and one in the right hand. And his full responsibility is just to control those, while the other crew try to troubleshoot, talk with air traffic control, and figure out how they can get this bird down. And so they slowly make their way towards Sioux City Airport. You can see it's not easy, to put it mildly. And it's hard to convey kind of how incredibly difficult this would be to do. Because not only do you not have any of the normal control that you're used to, but there's a huge amount of time between when you actually change an engine until the engine setting, until the engine spools up, and until this results in a change in the airplane. So it's extremely, extremely difficult. But they managed to approach the airport. They tried to keep it stable. It's a miracle that they even get close, honestly. And there's a great bit at the end where air traffic control tells them that you're cleared for any runway. And Captain Haynes replies, "Oh, you want to be particular and make it a runway, huh?" So this is a picture of the actual airplane right before it's about to hit the ground during this accident. And they managed to line up with a runway, but sadly the right wing kind of drops and they don't have time to correct it before they get to the runway. And so the airplane ends up flipping over, catching on fire, and breaking into parts, like on the airport, or in the airport. And so because of that, quite a few people die. So among the 296 people on board, 112 of them die. But that still means that over half of those on board, 184 people, survived something that should have been completely unsurvivable. And I really mean that when I'm saying that this should be unsurvivable, because as a part of the investigation into the accident, experienced test pilot crews, they tried to reproduce any sort of survivable landing under these conditions in the simulator, and not a single crew managed to do it. The only one that did was the crew that was in the airplane on that day. And so this performance, for good reason, is considered one of the most impressive in the history of aviation. And the highlight here is how they cooperated. But the captain realized immediately that he needs to get help from the passenger, and the way that they worked together and used all 4 people in the cockpit very efficiently to troubleshoot and kind of make their way down to the ground in the best way that they could. And so all of the pilots survived. And there's a really good quote from Captain Haynes in an interview that he did a few years later, where he said that the preparation that paid off for the crew was something called cockpit resource management. Up until 1980, we kind of worked on the concept that the captain was the authority of the aircraft. What he said goes. And we had 103 years of flying experience there in that cockpit, trying to get that airplane on the ground, and not 1 minute of which we had actually practiced under those conditions, any of us, with one minor exception. So why would I know more about getting that airplane on the ground than any of the other 3? If I hadn't used CRM, if we had not let everybody put their input in, it's certain that we wouldn't have made it. And CRM, or cockpit resource management, later generalized to crew resource management, is what I'm going to focus on in the first part of this talk. Because historically, as he said, air crews, they had a very clear hierarchical structure. They were based on ship crews, which also had a very clear hierarchy, where the captain was undisputedly at the top. And so CRM, this start as a term, kind of started to see use in the start of the 70s, mostly by researchers, a few aviators. And it's a set of principles and training procedures on interpersonal communication, leadership, decision-making, and situational awareness that are supposed to improve how a crew works. And this gained a lot of attention. Like the CRM, kind of attention around CRM skyrocketed after the Tenerife airport disaster in 1977. This is still today the worst aviation disaster that's ever happened. It was 2 747s colliding, and it's the deadliest one in history. And a primary factor for why this happened was that one of the planes had a completely dysfunctional crew environment with an overbearing captain. And so, of course, attention to CRM skyrocketed. And just a couple of years later, many airlines had introduced comprehensive training programs, and by the 90s, it was a global standard. And so, in aviation, the main goal is always to promote safety, right? And I want to focus on one part of CRM that's also directly applicable to us, even if our industry is not nearly as safety critical as aviation is. And that part of CRM is fostering what we know as psychological safety. So let's do a show of hands. Who here has a relationship with the word psychological safety? Okay, roughly half of you. There's a great definition by Harvard professor Amy Edmondson, which says that psychological safety is the shared belief held by members of a team that the team is safe for interpersonal risk-taking. And so interpersonal risk-taking is stuff like asking stupid questions, asking for clarification or questioning assumptions that are held by the team, or sharing differing opinions or admitting mistakes, right? All of that is interpersonal risk. And so these are things that we know are important, but they're often very difficult to do. And so psychological safety hasn't really been a thing in IT for that long, like relatively speaking. It really became a hot topic with a study that Google did called Project Aristotle. This started in 2012. It was a huge sort of research project that they did internally to figure out why some teams performed very well while some performed badly. And so they followed 180 teams. They used a bunch of different factors to categorize them as high performing or low performing, and gathered all sorts of theories based on their conventional wisdom on why some perform well and why some perform badly. And so they looked, for example, at the interest and types of motivation that people in teams responded to, whether they socialized outside the office, whether they had similar educational backgrounds or personalities. But the interesting thing was that none of this showed any difference in their results. It seemed like the who part of the equation was completely irrelevant. But what they did find was that there was something which showed a really clear correlation with high performance. And that was group norms, and specifically group norms related to interpersonal risk-taking. So in other words, the teams that had a high sense of psychological safety, where it was perceived as safe to take these interpersonal risks, generally performed much better than the teams where that was not the case. And so we have some guidelines based on this sort of project and psychological safety. But the point of this talk is not to go into the guidelines from the IT industry, but we want to look at the guidelines from the aviation industry, right? And so this is where we come back to CRM, because it turns out, this might be obvious, that this sort of culture is also really, really important for safety. Because if you have a very young member of a cabin crew who just heard a strange noise, for example, and doesn't know whether to report it, or maybe the first officer notices that the captain, who's the head pilot of the entire airline, might have just made a mistake. Like, both of those situations involve a large degree of interpersonal risk. And so both our industry and aviation are very motivated to achieve this sort of goal for different reasons, but it's the same goal. And so with the motivation out of the way, how does aviation actually do this? And so the first point, and something that I really hope that those of you in leadership positions remember, is that this culture has to start at the top. In aviation, creating this sort of environment is an explicit part of the captain's responsibility. It's an explicit part of their job. And for us, it's not necessarily as clear who like the leader of a team is. You might have a team lead, a tech lead, or just a senior that people look up to. But I think if that applies to you, it's really important that you realize that this is a part of your responsibility. This needs to start with you. And so I'm very lucky that in my team, both the team lead, the tech lead, and the most senior developer, who are all different people, are very good at this. And so we have this sort of environment where it feels safe to experiment. And I think that's a big reason for why we have been known as high performers in our organization. But okay, good, you know that it's your responsibility, but how do you actually foster this in a team? The most important thing you can do is to reduce the power difference. Another way to do this is to flatten, or another way to say this is to flatten the authority gradient. So you want to reduce the perceived power between the most powerful and the least powerful person in the team. And so let's say that you make a mistake, for example, as a leader, or you realize that you don't know something. In both of these situations, you suddenly have an opportunity to flatten that authority gradient. And so another way to do this is, and this might sound a little bit counterintuitive, but to communicate expectations to juniors. And this is something that I've heard captains in aviation do with very good success to young members of the crew. It's important to word this carefully. Like, you don't want to just tell someone that I expect a lot of you. That might have the opposite effect. But if you tell a new member of the team that from day one, they're an important part of the team, their skills are important, their knowledge is important, and their feedback and ideas is very important, and they need to contribute them. That, instead of putting kind of this, I think, unrealistic pressure, it kind of empowers someone instead, right? Like, it shows them that I'm genuinely important here. I need to speak up with my ideas. And so the next point I have here is to talk about feedback. I mentioned feedback just briefly now. And this can mean a bunch of different things. Inviting feedback is one part of it, and that can happen as a sort of general recommendation. You don't need to be a leader to do this. This goes for everyone. I think if you invite feedback and you're given feedback, that kind of helps create this sort of environment, right? And an example from my team, which is, I think, the best way that I personally have seen this been used, is my team lead. Because quite often after she has had a meeting, if she felt that it didn't really go well, that like she was leading the meeting and felt that we didn't really achieve the goals that we wanted to do, she'll take me aside or someone else aside and ask, what could I have done better there? I feel like that kind of didn't stay on the track that I wanted it to do. Like, did you see anything that I could have done differently? And so not only does that show vulnerability on her part, it shows me that she's, not infallible, but it also tells me that my judgment is valuable. And I can tell you from personal experience that after this, I've wanted to contribute more. I've wanted to kind of, give feedback and to partake in discussions and these sorts of things. And so I could have just written invite feedback if this was everything I was going to say, but I've written talk about. And that's because it can also be really useful to talk about how to give feedback. And so air crews, they have specific training for this. For example, to voice concerns, they use something called graded assertiveness. And so this is a tool that's used for raising concerns with increasing assertiveness, right? And then hopefully people will take that concern to heart, but if they don't, then you increase the assertiveness. This, I think, is overkill for most of us, but I want to give you a concrete example with a real model just so we can kind of see how it works. And so we're going to use the PACE model. This was developed in the wake of the Tenerife air disaster. It's also used extensively in, for example, medicine now. And let's say that, or let's kind of set the stage here. We are working on a Next.js app. I'm the person who's responsible for shipping it. And a CVE has just been published about an exploit that lets people bypass the authorization by just setting a header. Obviously hypothetical, could never happen. But yeah, and so we have a client, it's a web store, and the client has imposed sort of like a change freeze on us around Black Friday because they're terrified that if we push a new version, something might break and they'll lose sales, right? And last year, I made the mistake of authorizing a change during that change freeze. Everything broke and they lost a bunch of money. So I really don't want to do that again. And you've just read about this CVE and you think it might affect us. And you want to alert me, who's responsible for shipping this, right? That we should probably update our thing. So that's the stage. So let's look at how you do that following this framework. You'd start by asking a probing question. So this is kind of the most careful way of giving a concern, right? So you could say something like, I saw that there's a pretty severe vulnerability with like the middleware in Next.js. Do we know if that affects us? That sounds pretty serious. Hopefully that should work, but I'm stubborn, so it doesn't. And so you escalate it to the next stage, alert. And so here, instead of just asking kind of a curious question, you say that, I'm worried that this might affect us, actually, and that it might give people access to our internal admin pages. I think we should look into this. And I'm still not listening, just for the sake of experiment. So you go to the next level, challenge. So at that point, you tell me that we have to patch this. This is a critical vulnerability, and our admin page will be accessible. And even if even that doesn't work, you escalate it to an emergency. And so you say something like, this is a critical vulnerability. I'm taking it to the CEO or to the client or whoever if we don't do something about it, right? So then you escalate it to an emergency. Of course, the situation or the goal is that the situation should never go that far. But the point is that if it does, then you have tools and you know what you can do to communicate there. And so as I said, I think this is overkill for us. I'm not in situations like this very often, thankfully. But there are other frameworks for feedback as well. And so something that we're using in our team is the Moscow framework. And so these letters stand for 4 categories. There are 6 letters here, 4 categories, but the O's are just to make it pronounceable. So this stands for must, should, could, and won't. And so this is basically just a way to qualify how important some feedback is. And we use this in our code reviews. So when we leave a comment, we'll prefix it with one of these letters to kind of communicate how important something is. Because at that point, you can actually include as many nitpicks as you want, as long as you make it clear that I'm not expecting you to fix this. I just would like to share this other way that I thought of doing this. And so this isn't really something that we even decided to use. It's just, we read a blog post about it, and everyone liked it so much that we started using it. It's been great, so we've kept using it. And so the point here isn't really that any one of these models is a silver bullet, but rather that talking about how to give feedback can be very nice, as well as, of course, talking about when to give feedback. And so this is really important to create this sort of team environment, having this sort of feedback culture. Finally, I would like to encourage you to think aloud more often. This is something that pilots do all the time. If you watch a video from a cockpit, you will see that they narrate their actions and their thoughts constantly. And so that's good for multiple reasons. One is that it helps spread understanding, right? If one person has some sort of understanding in their head, it helps spread that to the others. But in addition to that, it also gives others a chance to interject if they spot an error, if they spot a misunderstanding, if they spot even a good point, right? Like it gives chances to kind of start working together on a process instead of just having it inside the head of one person. And so I think, at least for me, I would do well to think aloud more often during design discussions, architectural discussions, like standing there with a whiteboard, or just stuff like pair programming. So with that, we're through our first chapter. And the next one is about the remarkable attitudes that aviation has to skill development and retainment, and learning and knowledge creation. Or in one word, proficiency. And so, like the last chapter, I'm going to start this one with a case study. But unlike the last chapter, it's not a story of procedures working well, and it's not a story of heroic efforts, but rather the opposite. This is the story of Asiana Airlines 214. So this was a flight from Seoul to San Francisco on the 6th of July, 2013. And I actually remember this in the news. Some of you might too. And there were 307 people on board. Sadly, 3 of them passed away in this accident because it should have been 0. And this was operated by a Boeing 777, quite a modern aircraft that has an outstanding safety record. And the aircraft in question at the day had absolutely no mechanical issues. It was working as intended. So there were a crew of 4 pilots, 2 main pilots and 2 relief pilots. So the main pilots, they flew the takeoff and the landing, and then the relief pilots flew a little bit in between because it was such a long flight. And so the captain of the main crew, who was the pilot flying when this accident happened, was actually doing his initial training to be a 777 captain at the time. And so because of that, his first officer wasn't just a normal first officer, it was someone who was an instructor who could kind of evaluate how the captain was doing. And so the flight was completely uneventful until the approach. There was great weather, and the only irregularity was that the instrument landing system of the runway that they were supposed to use was out of service. And so an instrument landing system, or ILS, consists of 2 parts. The first one is the localizer. This helps guide the planes in horizontally, so make sure that it's not too far left, not too far right. And this one was working as intended on the day. But the second part, the glide scope, was out of service. And this is the part that helps the planes fly in vertically. And so it helps make sure that the planes are not too high or not too low. And so this isn't really a problem at all. It meant that the pilots were given a visual approach instead, which is totally normal procedure. It's something that pilots do all the time. But that means that they don't have this sort of precision system to help guide them down. They have to either manually hand fly the plane to make sure that they stay on this descent path, or manually control the autopilot to make sure that their descent rate is correct. And the recommended procedure in Asiana Airlines at the time was to maximize autopilot usage because it was believed that this is safer. And while it's true that increased autopilot usage and better autopilots has been very, very important for aviation safety, this is also about to play a big role in the accident that's about to happen. And so the plane ends up slowly drifting a little bit from their path. They end up quite high. It's not really a problem, like this happens all the time for a multitude of reasons. All it means is that the pilot needs to increase their descent rate a little bit. But because of a misunderstanding for the pilots in how the autopilot works, they actually don't really manage to do this. It ends up being even higher and getting even closer, right? So at this point, you might want to go around, but it's still savable, honestly. And so the captain in training decides to hand fly the aircraft instead. To me, this seems like a pretty sane decision. You want to take more manual control of the aircraft and make sure that you get down in time. But the crucial thing here is that as he starts hand flying the airplane, he still thinks that the engines are controlled by the autopilot. And usually that would be the case, but because of a very specific combination of states that they've managed to induce in the autopilot, it's actually not. So they're just sitting at idle, which is fine for now, but might become a problem later. And so a combination of hand flying and idle engines means that they actually catch up with the descent path and end up a little bit too low. And they realize that they're low, they're talking about it, but they don't realize that their speed is rapidly dropping. They don't realize that the engines are not spooling up. And so this is kind of remarkable, because I think most pilots will tell you that this is something you develop an intuitive feeling for quite quickly, sort of the energy states of the plane. And none of the pilots in this case realize what's happening. There are multiple reasons for that. Fatigue is one of them. Stress due to the initial training might be another. But the accident investigation concluded that a major factor for why they probably didn't realize was this lack of recent experience with manual flying due to the procedure in Asiana Airlines. And so the speed gets as low as 103 knots, which is an incredible 34 knots or 60 kilometers an hour below the minimum speed for this approach. And they finally realize what's happening and they power up the engines, but at that point it's too late. And the tail of the airplane strikes the seawall in front of the runway. And so it skids along the runway and it comes to a stop next to the runway on the grass. And so this happened due to a combination of factors. A lot of them had to do with sort of the technical specifics of how the autopilot works on the 777. And there were a lot of recommendations that came out of this. A lot of them were aimed at Boeing and at operators of the 777 to make sure the pilots didn't misunderstand these systems. But there's one recommendation that was made to Asiana Airlines, which really stands out to me, which says to modify your automation policy to provide for more manual flights, both in training and in line operation, to improve pilot proficiency. And this didn't end up being a wake-up call for just Asiana Airlines. It ended up spreading kind of as a wave in the whole aviation industry. They all saw this and wanted to avoid something happening in their own airline, right? And so this led to a bunch of changes in training and operations that were aimed at maintaining the basic stuff, the manual flight. And so automation compliance and automation dependency are seen as big dangers in aviation. And I guess that at this point, some of you can probably see where this parallel is going. And so this isn't really an AI talk. I'm not here to be a prophet or a doomsayer, but there's a very important and topical lesson here that I think we need to go through. I even got to experience this myself recently, and this guy's a little bit distracting, so I think we're going to go to a 2D version. But yeah, so I've been experimenting with AI code tools for the past couple of years, like a lot of you. And I started using Copilot when it came out. I started using it for work after a little while, and I was very impressed. To me, it made coding feel totally effortless. I suspect that's because it was. And of course, it didn't make me forget how like React works or anything, right? But I noticed that it kind of made my manual skills atrophy. I felt like my brain was being a little slower, like my skills were a little bit rusty. And so this was just Copilot, which is effectively just a good autocomplete. I don't really know what would have happened if I had full-time change to like a full AI IDE like Cursor or something. But what I did was I just turned it off. Not sure if it's the right choice because it's a useful tool still. So I'm not really sure what I'm supposed to do with this, but I turned it off and I noticed that my skills came back pretty quickly, and that was a good feeling, so I've kept it off. Because I hated this feeling that I was losing something, right? And recently I read a blog post that had a really good word for what that something was. Fingerspitzengefühl. So this is obviously a very aggressively German word. And it's become a loan word in English. For those of you who speak Norwegian, you can probably see that it translates literally to fingertips feeling. And what it actually describes is sort of intuitive abilities, instinct, and the things that you need to do things effortlessly. And so the blog post likened it with driving a car on the highway without actually having to think about driving the car. You can also see it as what you need to effortlessly write out syntax or intuitively sensing the energy state of your airplane. And so because of this, the aviation industry places huge importance on recent practice. And I think we need to recognize this too, especially with the advent of AI tools. It's easier for us than ever to kind of have our manual skills atrophy. And so if you recognize the feeling that I was describing, try turning Copilot or whatever you're using off. Just see how that feels. There's also some research into how generative AI tools kind of shift our critical thinking. There's a study by Microsoft and Carnegie Mellon, which came out a few months ago, which found that critical thinking shifts from information gathering to information verification. Instead of spending our critical thinking doing problem solving, we spend it integrating the response from the AI. And instead of executing the task, we steward the task executor, which is the AI in this case. And so this is based on self-reported data, so it's difficult to draw sort of hard conclusions from this. But the point here is that there are clearly consequences to these sorts of tools that we might not be completely expecting, right? And I don't know about you, but those skills on the left, they feel pretty important for me to do my job. So I'd really like to maintain them. And so I've talked about recent practice in normal operations, your bread and butter. We're going to do a tiny detour to the stuff that's not your normal operations, so your non-normal operations, as they're called in aviation. And so shocker, this is another thing that aviation takes very seriously. So seriously, in fact, that pilots roughly yearly have to jump into one of these bad boys and practice situations that will virtually never occur. And this is a so-called level D, or full flight simulator. It costs roughly as much as the airplane that it simulates. And luckily for us, we can practice non-normal situations too, and we don't even need a $20 million building-sized stormtrooper helmet to do it. And so there's a famous bit of wisdom in our industry when it comes to backups, which goes that if you have a backup and you haven't tested restoring from it, you don't have a backup. And so that's a great example of a non-normal situation that you want to simulate. One reason for that is that you test all the technical aspects, which is important, but I can also guarantee you that if you have to restore from a backup at 11:30 at night because some engineer RF'd your entire production database, you're going to be very happy that you have practice. And so, of course, this doesn't go just for backup restores. It can go for things like very, very high traffic or a machine going down in your server room. And so I won't spend that much more time on this. You know you're supposed to practice emergencies. I know I'm supposed to practice emergencies. I have a file server sitting at home running RAID, and I've never practiced restoring from a dead drive. So let's move on. And so the most remarkable thing to me about aviation's attitude to sort of knowledge and learning isn't the things that I just talked about individual proficiency. It's actually the stuff that has to do with proficiency in the field as a whole. And so there's a macabre saying in the aviation industry that goes something like, today's pilots stand on the shoulders of their dead colleagues. Sounds a bit strange, but it's completely true. Because the reason that we have today's procedures and regulations which make flying so safe is because every accident that's ever happened anywhere in the world has been studied and learned from in a way that makes aviation safer for everyone today. And so think about that. Like, an entire industry has managed to come together across borders and cultivate this unified base of knowledge that benefits everyone. Imagine if that was the case for developers, like this level of seriousness. Every time a serious outage happens, a team comes in, sent in by the state, they study the incident for 3 years, produce a 200-page report with 9 takeaways that get circulated into the procedures and guidelines of every software team in the entire world automatically. That's a little bit beyond the scope of this talk. But I want to talk about the method that's used to gather this knowledge. Accident investigation. And so in aviation, a team really does show up and do that. In the US, the team is from the NTSB, the National Transport Safety Board, and in Norway, they're from the NSIA, the Norwegian Safety Investigation Authority. And the result of an investigation like this, which usually takes years, is a report. And so this is a report on an incident that happened in 2020, where a plane lost both of its engines momentarily due to very severe icing conditions. The engine started automatically after just a few seconds, and so everyone was fine. Like, this didn't end up as an accident, but it's still a dramatic incident, right? And so this resulted, the investigation resulted in this report. It's 123 pages that go into intense detail on everything from exactly what happened to the way that the crew were briefed on the weather that morning. And so at the end of this report, you find 3 concrete takeaways. One is to the manufacturer of the airplane to update their documentation regarding how the engines of the airplane handle severe icing conditions. And the two others are to the Norwegian and European aviation safety agencies regarding live weather detection and standardization of icing terminology. And so the interesting thing is that these are findings that won't just impact Widerøe, they won't just impact Norway, but the whole world, all the operators of this sort of plane and everyone who flies in severe icing conditions. And this happens with every incident. And so the obvious parallel here in our industry are learning reports, or postmortems, as some people call them. Now, I prefer learning reports because they sound a little bit less severe, but both are fine, it doesn't really matter. And so I'm curious, who here does postmortems or learning reports as a part of their either unofficial or official procedure? Okay, so a little bit under half, I think. We do this in our team. We've done it for a couple of years, and I'm sure that it's directly resulted in less downtime in our applications. An example of that is that we started doing this, and we took some important numbers. We checked how long it took us to notice that our application was down, and we checked how long it took us to fix it after we had noticed that it was down. And we saw a pattern developing pretty quickly that the time to detection was about 10 times bigger than the time to solve. So at that point, it's pretty obvious what you want to spend your energy on, right? And so because of that, we spent a bunch of time, instead of improving our logging, improving our observability that would help us fix a broken application, we focused on improving our alerts. So that because of that now, we get alerts directly to Slack. If something goes down, we have automatic health checks, and we have like big monitors in our office that give us a live status at all times. And so that's made us catch incidents much, much quicker afterwards. And so what I want to do in this part is look at some of the principles that aviation use in accident investigations and see what we can learn from them. And so the first one, this is where I finally get to talk about the titular cheese of this talk. And I think this is an NDC first, but I actually have a packet of cheese that I'm going to open specifically for this bullet points. Because I want to talk about the Swiss cheese model. And so this is a risk analysis model that's had a huge impact on many industries. It's used in a bunch of different engineering industries. It's used quite extensively in cybersecurity. And it's the standard in aviation for how accident causation is viewed. I think this is also just generally quite useful. For me, it's the sort of thing that kind of rewired my brain when I learned about it to view causal analysis and causation differently. And it's a model that was developed by British psychology professor James Reason. He's quite relevant for this talk, so relevant that he's going to show up in the next bullet point also. But the point here is that he draws a parallel between Swiss cheese, or layers of slices of a Swiss cheese. So we'll take this out. And so a slice of a Swiss cheese and the layer in a system that could prevent an error or an accident from happening. And so none of these layers in our systems are perfect, right? They all have weaknesses, which are represented by the holes in the Swiss cheese. And so when you want to model, and let's see if I can do this. When you want to model a system, what you do is you take multiple of these slices, you put them behind each other, and you see where the holes line up, where a sort of error or an accident might pass through all of your layers, right? Because that's when it gets really scary. And so I don't have enough hands to show you a full system, so we're going to do this digitally instead. And look at just a simplified example of how we might prevent an important bug from entering our product. So the first layer we could consider to be local testing, for example. So hopefully the person who's about to introduce the bug notices in their local testing and gets rid of it. If that doesn't work, maybe it gets caught in code review, maybe it gets caught by automated tests, or maybe by a canary release that we give to a small percentage of our users. And so most bugs are going to be caught pretty early in this process somewhere. And when a bug makes it all the way through, and you use this model to look at your system, I can guarantee you that you're going to see many more of these layers than you thought existed. And so this is really, really useful when you want to figure out what the actual causes of something is. It's also really useful when you want to decide what to do about it afterwards, because you can either choose to try to improve a layer, or as the model kind of points out, impossible to make a layer perfect. So maybe you want to include different layers, that like more different layers instead, in the hope that they will catch the errors as they're about to happen. So use the power of Swiss cheese. The next is to embrace a concept called just culture. And so this is a fundamental part of how aviation treats mistakes. I think it's a fundamental part of how a lot of us treat mistakes as well, at least I hope so. Again, developed mostly by James Reason, smart guy. And the point here is to kind of believe that mistakes are always the result of a faulty organizational culture or a procedure. So even if you have human error, you have to ask, why is there human error, right? And so unless there was misconduct or gross negligence, it means that there has to be an underlying issue here. And in that case, the situation is blameless, and the entire point is to figure out what kind of systems can you introduce, what kind of systems can you change to make sure that this human error can't happen again. And I genuinely believe that having this sort of mindset is the only way to get to the root cause in a lot of incidents, because it's very easy just to get caught up on human error. Like in the GitLab incident that I talked about, human error, the engineer literally RMRF the production database. Like that shouldn't happen, right? But why was it allowed to happen is the question that you really need to ask. Because another engineer, even if it's a smart engineer, might do the exact same thing. And so accountability in the system still exists, but it's based on behavior rather than outcome. And so the GitLab incident is actually a really good example of that, because the engineer wasn't punished at all, but actually rewarded for the way that they dealt with this accident after it happened. The next is something that might seem a little bit obvious, but it's kind of an important mindset shift still. And that is to not just learn from your mistakes, but learn from your decisions. Because when you're doing a learning report or a postmortem, it's very easy to just look at the things that went wrong. Like this is where things went to hell, right? But it's also very important to look at all the mitigating factors. Like what made this not go worse? And in every single aviation accident report that I've read, which is probably more than the average person, which I think that number is quite close to zero, the average. But in every single report that I've read, there's been a significant portion dedicated to mitigating factors, because those are also really important. Maybe someone did something that wasn't procedure, but really smart and should be procedure. If you're just looking at mistakes, you're not going to be able to catch those things. The next thing, and the final point on this slide, is that you need to spread this knowledge, of course. And we might not have a planet-wide, like automatic, amazing system for it, but we should at least spread it to other teams, spread it in our sections, or maybe even in our whole companies. It depends on your situation. Our strategy in our team is just to find the biggest Slack channel that's sort of relevant and post the learning report there. And I'm pretty sure that people have learned from our mistakes that way. The thing that I know definitely has happened is that other teams have started doing learning reports because they've seen that we do them and they think it's a good idea. Yeah, so make sure to spread your knowledge. Finally, we're at the third and final part of this talk, where we're going to talk about procedure. And so procedure is how aviation applies this sort of century of knowledge that it's built. And we could talk about a lot of different things. There's a lot of different parts of procedure in aviation that's interesting, but we're going to focus on the most iconic part of it, the checklist. When I say that word, how do you feel? Because if I tell you that every time that you build an API endpoint, you have to follow a bunch of manual steps every single time, or every time you leave a review on a PR, for example, you have to follow a long list of steps. Doesn't make you feel good, does it? Doesn't make me feel good. We have a contributing document, which is kind of exactly this in our repository. Pretty sure the last time that one was read was when we wrote it. Because coding is not as mechanical as flying an airplane, right? Like we're knowledge workers. We can't really use this sort of stuff. At least that's exactly how doctors felt when they were introduced to the idea of using checklists based on some early preliminary research that showed that it might be effective. And I feel like we have a high degree of like novel combinations of problems that we see every day, but compared to doctors, our work is quite routine. And because they see a completely staggering staggering number of combinations of problems, right? And I think like being a doctor is pretty much as far away from mechanical repetition as you can get. And so how could a lowly checklist possibly be helpful for them? There's a book about that. This, written by author Atul Gawande, who's a surgeon who worked for the World World Health Organization for a while. He was on a team which tried to create sort of general guidelines for surgery that could make surgery safer all over the world. And because they saw some promising examples of checklist use in different parts of the world, they wanted to give it a shot. And this is a really interesting book. They go into detail about how they talked with Boeing, how they talked with the construction industry, which both use checklists, on what makes a successful checklist, how you create a checklist, and the results that they saw. And fun fact, pretty much everything you can find online about applying checklists to new fields is based on stuff from that book, because it's literally the book on that topic. And so Gawande's team came up with a list of 16 items that was divided between 3 different check-in points. So one set of items was before the patient was put under anesthesia. The second was before an incision was made. And the third was before the patient left the room. And so this includes items such as making sure you have the right patient, making sure that the team has actually introduced themselves to each other so people know each other's names and roles, and counting the number of needles, sponges, and instruments to make sure they're not inside the patient after the surgery. And these are like literally 3 of the 16 items on that list. So do you think it worked? I mean, it would be a little bit strange for the guy to write a book about it, or for me to bring it to this talk if it didn't. So I think we can assume that it worked. But how much did it have of an impact? Well, they saw a 36% decrease in the number of complications just by starting to use this checklist, and a 47% decrease in mortality rate. And these numbers are so crazy that they weren't excited when they saw them. They were worried that they had fucked up their math. But it's true, like this is the results that they saw. And that's not just because checklists are really good at preventing errors. It's because they're also really good at another thing, which is managing complexity. Because fields like aviation and construction, which I briefly mentioned, and medicine, they have gotten vastly more complex in the recent decades. Because they all used to be fields where sort of one person could have an overview over everything that was happening. You had like the master surgeon or the master builder or the captain of the aircraft, right? But they've gotten so complex that you needed more and more specialization, and it's less and less common for a single person to kind of know everything that's needed. Sounds familiar? And so how does a checklist help manage complexity? It does it by getting rid of the dumb stuff for you. So I think the most common problem that bad checklists have is that they're not really a checklist at all. They're a to-do list. They try to kind of hold the hand of the user throughout the whole process, spelling out all the important steps of all the difficult procedures so that they can make sure they don't forget anything, right? But that's not what a checklist is good at doing. A checklist is good at offloading your brain so that you can stop thinking about the easy, important things and rather spend your energy thinking about the difficult, important things. And so let's make a checklist. First, we're going to go through a couple of meta points, sort of disclaimers. Both of these are non-negotiable according to the book. The first one is that it needs to be made by people who are going to use it. If it's going to be used by developers, it needs to be made by developers. Of course, you can have help from other people, but this is non-negotiable. The second one is that it needs to be tested in the real world. The guy who they talked to in Boeing, who's kind of the head of their checklist program, has said that every single first draft that he's ever seen has fallen apart in real-world testing, and so you need to iterate upon it based on real-world data. And so next, you have to identify a pause point. So this is when you stop what you're doing, you pick up your checklist, and you go through it. Sometimes this is very natural. If you're making a deployment checklist, maybe it's before you actually ship your package to the server. That might be when you do your pause point, but sometimes you just have to make up something. The next is that you have to choose what kind of checklist you want, whether you want a do-confirm checklist or a read-do checklist, because these are different types of checklist. A do-confirm checklist has users actually do the steps first and then go through the checklist and confirm that everything has been done. And so this is good for stuff where you just want to make sure that things have been done, right? And so it's kind of a safety net. And it's nice for high familiarity situations where you might want to work in parallel or the order of steps isn't really so important. The second type is a read-do checklist. And so in this case, you have to actually read out the step and do the step. Read out the step and do the step, and so on. And so this is useful when the order of the steps is very important, of course. But it's also nice in novel situations or high-stress situations, because in those types of situations, it might be difficult to kind of remember exactly what was done in a do-confirm checklist. And so the next part is this thing that I was kind of mentioning earlier, which I think is the most difficult part of making a good checklist, and that is to include only killer items. Because you don't want to make a to-do list, you want to make a checklist. And so what's a killer item? Let's plot everything that you could possibly put on a checklist on these two axes. So you have the likelihood of forgetting something and the consequence of forgetting something. I've put some colors on here. I've made kind of a bad flag. And the green here are the things that are routine or inconsequential or both. And so these are things you would never put on a checklist. The yellow are things where the consequence is still kind of low, or it's exceedingly rare that it happens. And so these are things that most likely you want to keep off to keep the checklist short, but that you might want to include on a case-by-case basis. So this leave up to interpretation. And then finally, you have the killer items in red. So these are the things that can be forgotten and are also very important to remember. So in aviation, it can be something like remembering to lower the landing gear. Probably not so easy to forget, but extremely important. So you're going to find this on every single landing checklist in the world. And stuff like making sure that anti-ice systems are on if it's required. In our industry, it might be something like making sure your SSH'd into the right server, again, GitLab, or making sure that you're building your application in production mode. This is based on something that I messed up once. I was quite new in our team, and we had some legacy applications that we were still building manually on our computers. We didn't have pipelines for those. And I was debugging something, I'd fixed the bug, and when I wanted to build the application for shipping it to production, I just Control-R'd back in my history, and I ran the build command again, of course, with the debug flag. So we got a log graph that was flat, and then had a vertical column, and then flat, because I had managed to increase the number of log messages with quite a lot of zeros. Quite a lot of zeros, so yeah. Next, this is something that's easy to forget. You should make sure to include communication steps on your checklist. These can be really useful if you have some sort of process that needs involvement from another group, or maybe another group just should know that it's happening. The next is quite self-explanatory. Make sure you have simple wording, precise language, short items. People are going to read these many times. You shouldn't burden them with a lot of words. And finally, it should be as short as possible and a maximum of 9 items. This is a little bit flexible. If you need it to be more, that's fine, but Boeing uses this as guidelines because that's kind of the limit of working memory. And so ironically, my last advice is to use this sparingly. Don't make checklists for everything. Checklists are extremely powerful in the right situations, but they're not great for all the others. And so if you don't have these killer items, a checklist might not be the correct solution. And another thing is that we're really fortunate that we get to automate a lot of these things. Like, we can automate a lot of things that they can't in medicine, for example. So if it's possible to just do something with an automation pipeline instead, of course, do it with automation. Don't expose someone to a checklist. And with that, we're through the last chapter of this talk. I've gone through a lot of different things. There's going to be a QR code at the end on the last slides in case you want to have sort of the main takeaways. But the point here is that it's not really crucial that you remember everything. My main hope is that I've piqued your curiosity, that you've seen something that you might be interested in experimenting with, or that you have some new ideas that you're excited about taking back to the office next week. And so I want to end this talk with an anecdote. This is a true story from an aviation conference, not totally unlike this one, held in the US about 25 years ago. And so there's the talk on crew safety, and the entire first row is filled with pilots from American Airlines. And 25 years ago, these guys, and they are mostly guys, are the absolute kings of the aviation world. So you cannot get cooler than being a pilot in American Airlines. And so the speaker is saying that the best air crews are in Western Europe and North America. And so, of course, a jackass in the front row decides to interject and ask, well, which one is it? Is it Western Europe or North America? And so the speaker says, I don't really want to distinguish. The point is that that's usually where the safest air crews are from. Well, come on, which one is it? And so the speaker says, well, if you really want to know, if I got to choose, I would like to have a Scandinavian crew. And I can guarantee you that not a single person on that front row spoke up for the rest of that talk. And so I tell you this not just because it's fun to poke fun at cocky Americans, but because there's an important point here. Because studies have shown that even when you control for factors such as GDP and number of flights, there's actually a correlation between aviation safety and the sort of natural power difference in a country's culture. And guess which countries have the lowest power differences in the world? It's the Scandinavian ones. And this is kind of the same thing that Google found leads to good development teams. And so we have an advantage here. We're very lucky to have this as a part of our culture. And I think that we should try to use this to be as good of colleagues as possible and to make the best development teams possible. Thank you very much.